All right, welcome to today's program, which presents an investigation into how mid-rise cold-form steel frame buildings perform when subjected to seismic loads and then burned. So if one isn't bad enough, then we inflict some additional pain. We're happy you could be with us today. My name is Larry Williams. I'm Executive Director of the Steel Framing Industry Association. We are the industry association for the cold-form steel framing industry. And we have membership that is the entire supply chain from steel producers, stud fabricators, tool and equipment and connector manufacturers, supplier distributors, design professionals, and contractors. And of course, we provide our members with a broad range of technical and marketing resources, research and development. We do code and legislative advocacies, have certification programs for stud and track connectors, contractors, and truss fabricators. This program is an example of the kind of programming we provide for our members and is one in a series of webinars that tackle topics that are relevant to managers today. Next week, we start a 3-part program on millennials with an expert who will guide attendees through how to attract, retain, and then develop and grow millennials into leaders in your companies. So if you're not an SFIA member, you should be. Joining is easy. Just visit us at cfsteel.org. The link is on the home page. That's CF Steel for coldformsteel.org. And there's additional information there. And of course, would be delighted to answer any questions and delighted to have you as members if you're not already. Just a couple of notes before we start the program today. Today's program is being recorded and the video will be available for viewing later in the members only section of the SFIA website. Again, that's CF Steel for coldformsteel.org. Now it's my pleasure to introduce today's presenter. Harry Jones is a principal with the firm DCI Engineers. The company has 13 offices throughout the Western United States. And Harry has a very deep and rich background in seismic and structural engineering for a variety of project types and spans over 35 years with project management experience that includes seismic rehab, historic preservation, medical, educational, commercial, and industrial facilities using a wide range of construction materials. So without further ado, then I would, again, it's my pleasure to introduce Harry.
Thank you, Larry. So this was a project, a research project that we did with Tara Hutchinson she's a professor at University of California, San Diego. And this was done on their outdoor shake table. We also work with SWS Building Systems and some other industry professionals to do this research. But let me first introduce myself. DCI, as Larry mentioned, we have 13 offices throughout the United States. We do a lot of cold form steel amongst other building systems as well. This is just a picture of the USD, University of San Diego's shake table. It's the largest shake table, outdoor shake table in the world. It's 25 by 40 feet. And so what's nice about it, since it's outdoors, you can build as tall as you want, and essentially perform real live experiments, testing real earthquakes that can occur. And it's actually it has horizontal actuators now, but it's being updated to have vertical actuators. So it's actually going to be able to essentially show all the earthquake forces that a building goes through, and then test it. So the overall concept for this study was we wanted to do a 6-story, and part of the justification for that obviously was wood. There's a lot of wood buildings up to 5 stories, and so we felt like going 6 stories was a way to demonstrate what you can do with cold form steel, which is sort of unique. And we picked a housing as sort of going as the model for how the building would be designed and would represent a multifamily housing building. The structural components were basically shearboard shear walls. There were interior quarter shear walls. There were some narrow ones on the outside. We put in a little bit of transverse shear walls, not so much because the shake table moves them in that direction, but just in case there's any torsion or anything like that. We used tension tie rod system, which went down through the whole building. We balloon framed the construction, which is typical for cold form steel. And then they actually the sheeting on the floor was actually the shearboard system. And then the design, you've obviously got to pick when you're doing a shake table, you've obviously got to pick a code that you're going to design it to, which was ASC 710 at that point. And then you got to pick a place. And so obviously you're doing something to test high seismic. So there's no better place than pick a site in downtown LA. And then the other critical thing is it's got to fit on the shake table. So you can sort of cantilever off of it and do some things to try to get it a little bigger. But we were able to ultimately set it up so that it all fit on there. This is and this is actually the footprint of the building. The grid lines you see are where the connectors are on the shake table. And so then we added quarter shear walls, which is, so this is, again, is representing a double loaded quarter. So a quarter down the middle. And then we try to be representative. Architects like windows, they like a lot of exterior space, balconies and stuff. So generally when engineers start designing these buildings, we rely mainly on the quarter walls, and then in the transverse direction, usually there are party walls that we can rely on. And then this is the sort of the party wall stuff that we put in that doesn't really get tested, but it's just there in case there's some kind of torsion in the building. And then we actually put a non-load bearing wall down the middle, and this was actually part of the reason for this was related to the fire test. In other words, we're going to set fire in a room here, and to create these different areas, we use the party walls or these non-bearing walls to do that. And so this is the typical framing system. This is like a typical plan, and you'll see there's mass plates. So one of the things about a building like this and a shake table test is that you really got to have a building that represents the mass that a real building is going to have, because the performance is all about how much mass you have in the building. If you build a really light building, then it's really not going to perform like a real building is. And since you can't put gypcrete and you can't put all the siding on, and that would be expensive, so you put these mass plates on that represent all the mass that you can't have. And then the other critical aspect of the design is making sure that you design the shear walls per code, and you don't over design them, because if you over design them, then you end up with an experiment that really doesn't help you. You want it to reflect the engineering that the structural engineer is going to do. If he's going to, the screw spacings and everything else like that for the shear walls needs to be dialed into that pretty well. So essentially you deal with the mass, you calculate how much the mass plates are going to be, and then you use that to back calculate the capacity of the shear walls, and you try to get as close as you can to the actual, so the building strength actually represents what it needs to meet code. We balloon framed. This is sort of just an example of the balloon framing with the track on the side and the studs coming across and connecting to a track. And then this was a typical shear wall elevation, which shows you can see the tie rod going all the way up through, and then there are compression posts on either side. And this is pretty standard particularly in high seismic, to do this kind of a system. The image on the right shows how the shearboard comes up, and then the shearboard, the gyp sheathing is taken off, and so the shearboard can go all the way up and tie into the floor diaphragm. And then here's just some pictures of the interior construction, how it was built. Again, you can see the tie rods, the joist, and the studs. This is just to give you a good example of how all that works. And so now the first video is going to be the actual construction, and you can see how it was built. So the thing that was tricky about it was at the bottom. The first floor really wants to be stick built because we need to have connectors that connect it to the shake table. And so you can tell from the video, particularly as we move along, that this was a pretty long process just to build the first floor. You know, because you're basically stick building, which is not the most efficient way to do cold form steel. And as we get through the first floor, then all of a sudden the panels start coming in, and this goes a lot faster. And then we just keep going up. So we're halfway up the building here at the third floor. So yeah, you can start to see the corridor, the edge of where the corridors are at the middle and the windows. So now the issue is about the response of the building. Now we have to look at the earthquake levels, and so there are a number of earthquake levels that we deal with. And so we're actually going to be subjected to a lot of earthquakes. There's going to be some 25% earthquakes, design level earthquakes, just to get us feel for how the building is performing in the periods. And then we're going to essentially increase those up to 50% of design level, which would represent a small earthquake, and then 100% of design level. And then we're going to go all the way up to what we would call an MCE earthquake level, which is 150% of a design level event. So what's important to understand is that when we do this, the design level earthquake is really 2/3 of an MCE, and really is, we would expect the performance to be at a life safety performance level. And you know, with sort of moderate loosening of connections and yielding of materials based on the design level earthquake event. But the building also is meant to be, when you design it for the 2/3 MCE, it is also, you're also anticipating it's going to meet collapse prevention for the really big earthquakes, the MCE. So for Los Angeles, the MCE would be somewhere around like a 7.2 Richter magnitude earthquake that would happen. And so for that, we would expect to see a lot more damage. We expect to see sheathing sheared off, members just yielded, and sort of significant damage to the building. But if it doesn't collapse, then people should not be killed by it. And so it's actually meeting what we engineers would like to see. And then immediate occupancy is something that is also looked at. And for this building, obviously it's a housing building, and so we aren't really looking at immediate occupancy. Okay, so then this is sort of my expectation. You know, again, I wouldn't expect to see damage to diaphragms because they're short spans. And then their transfer walls aren't going to really see any motion, so there shouldn't be damage there. I wouldn't expect to see damage to the tie-down system because that's designed for some pretty large forces, actually, in the earthquake. Again, no damage to compression posts because they're also designed for major forces. And then I would expect to see some limited damage to the short shear walls, but the diaphragm's pretty stiff, and so the corridor walls are really where we would expect to see some cracking of the gypsum board and on the shear board, and cracking of some of the non-structural walls around there. We'd expect to see some pretty good transient story drifts, which is really how much drifting in the building happens during the earthquake, and then some residual drifts as well. And actually, we would expect to see sort of more damage than you might with a normal building, just because we're subjecting it to multiple earthquakes. It's just it's going to be really raked over the coals. And so and then also the foundation is very rigid, because we're locked onto the table. A lot of times in the real world, foundations will rock, and that will actually help limit the damage a little bit in these buildings. So we're going to jump. We actually subjected it to some lower level earthquakes, but we're going to go ahead and jump to the MCE. So this is the big earthquake, and this is obviously before the fire. There hasn't been any fire testing on this. It's just been subjected to about 5 or 6 other earthquakes that are lower, and then this is when we get to the bigger one.
Oh, oh man, that's cool. Wow.
All right, Steve. Yeah.
So this is just to show you some examples of the damage for the lower level earthquakes that we saw. So this is 25% and 50% earthquakes, and you can see there's minor cracking of the sheetrock, but not significant damage, and you wouldn't really expect to see significant damage for these lower level events. This is EQ6, so this is the design level earthquake, and so there is a lot more cracking. This is where the shear wall was banging. The shear wall was banging into a non-shear wall element. That was part of that is a function of the panelized aspect of the construction. Again, doorways, you can start to see doorways having distortions, and so in an earthquake, obviously the doors can jam closed, which is not a very good thing to happen. And again, this is the shear wall banging into a non-structural wall. You can see for the big earthquake, we started getting some buckling of the track. This is where the shear board chip was taken off the shear board to connect it into the diaphragm, and so that's started to buckle as well. And then this is the corners of the shear walls are starting to buckle a little bit here. Again, no real damage to the tie rods or the compression posts. They're all in very good shape. Okay, so summary. So for the service level earthquakes, which is really the small ones, there's minimal damage. Everything was pretty much elastic in the period. The period's still actually pretty stiff for this building. Design level earthquake, quarter walls are damaged at level 3 and 4. Started to get some gypsum panel crushing, some fastener withdrawal, and a story drifts of 1%. Period increased actually by 50% up to 0.5 seconds, and then this is the MCE, and so we had steel sheathing buckling near attachment points and quarter walls, and a story drifts of 1.5%. But the interesting thing was it was all repairable damage, which is not necessarily what you would expect for a building that was only going to meet collapse prevention. You would expect more damage than that, and potentially non-repairable damage as a result. So then we did after doing that, then we did the fire test, and the fire test was pretty extensive too, actually. You can see this was sort of the criteria. They picked the floors where we saw the most drift and likely the most comprehensive damage to from this earthquake. And then we did fires in a number of places, and the fires actually got pretty intense because there was a lot of openings, no windows and stuff, and so it was almost like a chimney effect. And so this is some pictures of the damage that the fire caused. We're starting literally to peel off the sheetrock, some pretty high temperatures. This sort of shows you how the fire came out the sides of the building pretty extensively. Obviously, there were fire trucks around when they were doing this to help make sure everything was safe. And so then we did 2 tests. One of them was a really small earthquake, 25%, just to sort of test it, and then we subjected it to the MCE, which is the maximum considered earthquake, of 150% of the design level. So now there's a question for the audience. So, and you can sort of write in your answer, but how many of you think it's going to be a small impact, which is to say that there's not a whole lot of impact on the fire? How many think it's a medium impact, and how many of you think that the building actually falls down in the event? So, so now I'm going to show you a couple more videos. The first videos is a view of what's going on inside the building, and then afterwards we'll do a perspective from the outside. So this is actually Sarah Hutchison's daughter playing, or Tara Hutchison's daughter playing the piano in the background on these. So these are just looking at it from different rooms. You can see that it'd be pretty scary to be inside the building. You can hear the horn. They always play the horn before they run the earthquake, just to let everybody know that it's starting, the shake table's starting to operate. So a lot of cameras in this building. All right,
Thanks.
that's the last one. So now you can jump to the next slide, which should be the exterior. So with that video, you can see basically that the whole second floor story hinged. Essentially, the only thing that kept the building realistically from falling down is the tie rods that were still intact and were able to hold it up. So you can see the damage inside was pretty significant in terms of, I mean, total failure of the shear walls. Essentially, they've totally disconnected. You know, like I said, the tie rods are still intact, and the compression posts are still doing very well. And that's really what allowed the building to keep from falling over. Otherwise, it would have fallen. It would have fallen down. And you can see there was the drifts at that level were 7.3 inches, and the top of the building was at 10 inches. So it was 6% is a pretty large amount of drift in a building. So you know, it was a good lesson to learn about sort of tie rods and how well they're able to perform and provide support for buildings. So the fire test, she had the degradation of the gyp wallboard on the steel sheathing, and that really led to the loss of structural strength. Obviously, the shearboard sheathing really needs we really need the gyp to stay intact to it for it to perform at the level that we really want. So loss of rigidity in the floor system due to the degradation of gypsum on top led to the floor bowing. And so we also had some floor bowing. And then after earthquake aftershocks significantly hit the demands on the building. The only thing I would point out from the experiment, though, is that the fire, if you think about it, there's a lot of fire in the building. And so this really would be more representative of a building where there had been a major fire. In other words, it burned a big portion of the building. If it was in one room, then the other areas of the building would be relatively intact and able to perform well during an earthquake. But this, because we're doing this as a shake table test and we can only do a small footprint of building, and then we do the fires, that can have a big, has a big impact on the overall building and not just a portion of the building. So, you know, again, we had full shear hinging on level 2, but the tension tie rods held things together. So overall findings. The earthquake performance of the CS building with the shear board, it was actually significantly better than expected, you know, for, you know, obviously the pre-fire performance. The damage was pretty minimal even for the really big earthquake, we were, I feel we were performing a lot better than a collapse prevention only building would be considered. The overall, the balloon frame construction and the tie downs performed well, and they seem to be proven to be a good building system for cold form steel buildings. And then the other, obviously, is that the fire in a building like this could represent a significant hazard. So from aftershocks, since the damage, you'll have damage at, if it's in a fire, you're likely to have damage in a floor, in an area of the floor, and that can create a soft story and create shear hinging. But I mean, the only issue I would also add, though, is that technically the building didn't fall down. So in that sense, that's a very positive thing for a building to go through that kind of a fire and that kind of damage and not fall down, even if it stays up through a sort of a secondary element. Okay, that's my presentation. I'll be happy to answer any questions that people may have now. If you've
Okay, thank you, Harry. We, despite some technical issues there, I think we survived. We survived that one.
Yeah.
But again, we did get some good questions here. I think that I'll take a couple here. The first is relative to the seismic loads that were imposed on the building. What would be an equivalent on the Richter scale?
Well, on the Richter scale, the MCE earthquake the Richter will vary depending on the area of the country you're in. And so in downtown LA, the MCE is generally like a 7.2 or even a 7.25. So that would have been the MCE, which was the big earthquake that you were seeing.
Okay, very good. Next question is, what kind of result would you anticipate from these tests if the building was fully loaded with furniture, refrigerators, people, etc.?
Generally in an earthquake, it's the mass that's tied into the building. You can get things shaken around. We actually did have there was some of that in there. There was stoves. There were some water heaters, and so we were also testing the strapping for those things. Again, this was somewhat sponsored by the insurance companies, and so they paid for some of that. There was a case where the water heater actually broke loose in the earthquake and actually leaked water over the building. But I would not expect a significant increase in the structural damage, although the interior, stuff could get banged up and beat up a little bit from furniture and things like that loaded in the building.
All right, thank you. Next question is, how would a cold form steel building work in a design element type without pre-qualified connections? In countries in the third world, because in countries in the third world, they don't have a pre-qualified kind of connection industry.
I think that that's a good question. I think that I think it depends a lot on how the engineer designs it and what they use. I do think that there should be some discussion about some of the code requirements that are in the United States in terms of designing the compression posts and stuff like that for Omega. Is that really a necessary thing to happen? So I think there may be scenarios in third world countries where you could design a building that may not say stand up to everything that this building stood up to, but it would be sufficient for those jurisdictions. So I think a lot of it is just making sure that whoever is designing it and detailing it really understands how the performance is going to be impacted and use good detailing and connections. Again, like I said, balloon framing it, particularly when you get to multiple stories, becomes an important part of it. So it's really just about utilizing good details. I don't think they all have to be fully proven and tested in a real situation. I think you can achieve good details if the engineer has seen how things perform and understands what works and what doesn't.
Very good. Also, another question in regarding to the shear system. This particular design used shear board for the shear wall panel. Any other solutions that would be effective in this kind of test or this kind of application?
Yeah, I mean, obviously the other option that you do with cold form steel is to do steel plate shear walls, and we've done a number of buildings that way, and so that could clearly be an option. You could look at strapping. I don't think that would perform as well. I think it would be interesting to do the similar test, but use steel plate shear walls and see how they perform in a building like this. But those are really the main two options that we would see for a building like this is either the shear board or the steel plate shear walls.
Good, thank you. All right, another question here. The first level of framing was stick frame. Since the studs were not seated, do you believe the screws at the top track of the wall connecting the studs were in shear? That's the first question. There's actually two here, so maybe I'll let you take that one.
Yeah, the stick framing it is tricky. I believe that they did seat the tracks as well as possible with the stick framing, and that you did end up with everything being in shear in the connections. Diego might know that better than me. He might be be able to answer that question better.
Yeah, and actually we have another member who is on the team who was actually involved in the wall fabrication and panelization of the system, Diego Rivera, and I'll just introduce Diego very quickly with the SWSO panel. And Diego, do you want to take that question?
Thank you for the introduction. I did hear everything. Great job, Harry. That's a great question. I think having the ability to have a compression table, and that's what we do in the shop, and being able to cover that gap, and you can see on that screw on the left on the picture, and not create anything more than what the radius of curvature of the track would allow you for that stud to fully seated on the track in stud connection. It eliminates any of those shear questions that we're asking. So stake framing, when you go to the high gauges that we were using there, it's really hard to get a 16 gauge stud embedded into a 14 gauge track or vice versa. You really have to understand the radius of curvature, and compression tables and panelization is the right answer for those techniques.
Yeah. One thing I would say though is that also in this building, where that becomes a bigger issue is obviously gravity loads. If you start to load a building up and all of a sudden they start to seat themselves, then that can create issues. And so in this building, we really didn't have the full load. The spans were pretty small because of the footprint of the building, and we weren't putting all the load on the building. So I think I'm not sure that would have impacted the testing all that much in that sense.
Very good, and you actually answered the follow-on question that he had. So good job.
Yeah.
Got a couple of other good questions here. One is, were hold downs considered at the end post instead of continuous tie rods?
DCI does a lot of cold form steel buildings, and we typically jump to tie rods just because we think it's a better system and it works better. So there may have been a little discussion about hold downs, but by and large, we also had Zone 4 was one of the industry sponsors, and so we used their system for the tie rods. And I just, generally, particularly in multi-frame housing, where you have big projects and multi-story like this, it gives you a much more concentric kind of load path. And so we didn't we didn't think long and hard about it. We jumped to the tie rod pretty quickly.
Okay, very good. Another question is, with the results from these tests, how many stories do you think the system could achieve?
That's a good question. You know, it would depend a lot on the building. Obviously, this is, you know, to be honest, this was a pretty, you know, small sliver of a building, as opposed to, you know, larger multifamily housing projects can easily be 100, 200 feet long. I think you could argue that you could go pretty tall with this kind of a system, and I think it's mainly limited by design loads. You know, we were pretty high, you know, loads for the shear board for this system based on the amount of shear wall we had in the building, and you know, our screw spacing was not we weren't as highly loaded as you could be, and so it would be easy to imagine you could go with shear board another, you know, say 3 or 4 stories and not overdo the shear board system. So I think it's with steel plate shear walls, you might be able to go a little higher, but because you can obviously adjust the sizing to achieve it. But I think it's really just a matter of what the design could be, what it could handle.
Okay, and I think you began to answer this next question, but it said that one of the viewers noticed that the shear board panel didn't go full height due to the ledger and the rim track. Does it affect the shear wall strength?
It doesn't really, and again, the reason is just that you don't want to put the rim track over the sheetrock, you know, and so you want to allow the steel plates to go through it. You know, the damage that you saw there was basically after they took the rim track off. Otherwise you wouldn't have been able to see that. But it wasn't like it just totally failed. It was mainly just oil canning of those plates. So I don't think that taking that sheetrock off in that area was a big deal, because you had the rim track over it. When the fire came and took the sheetrock off, and then there was nothing else over it, that's when you started to have ugly performance issues.
Yeah. And let's see, it looks like the last question that we have here so far in the queue is, if you have to choose between shear walls and tie rod systems versus a structural mixed brace frame, which would you choose and why?
You know, that goes to it's really, you know, a lot of times that's driven by cost. You know, I mean, there are some really good brace frame systems out there, and you could use them in a lot of places, and they would perform really well. Or you could do this system and it can perform well. It depends on just a lot on what the building is going to be used for and what the interior architecture looks like. You know, is there an opportunity to put that in there? You know, there are sometimes when we get to really, really tall cold form steel buildings, we'll do a shear wall core, and we'll put metal deck in and put concrete down and have a concrete diaphragm, and then we're not limited like we are on some of the other cases. To be honest, I would probably go to that type of a system if I was really in a situation where I needed to go higher and wanted to get and try to get maybe a little better performance. I'd be tempted to go that direction versus, you know, adding in a bunch of brace frames and then trying to tie everything together. That could be tricky.
When it comes to our world, let me give you a little thing right there. You know, I'm at the end where I see the cost. You know, we make money out of making cheaper buildings and going a lot faster. We're noticing, and it also comes from a lot of designs that we're doing a couple of buildings with ECI, that up to 3 stories we're actually able to replace the shear board with sheet metal and the rod system with a hold down system in between floors, and being able to acquire the same momentum or shear values on those shear walls. When we go past 3 stories, the tie rod is the most efficient one. We use HSS, Pacos, welded studs, and they become very inefficient in the cost. We're doing a 9-story building in downtown LA. We were forced to use brace frames just because of the requirements of building. So every project is different, but I'm with Larry. I mean, with Harry, the tie rod is probably the most efficient to the dollar in the efficiency when it comes to panelization and able to go faster.
Great, thank you. One last question, and that is, as a result of these tests, what do you see the path forward in terms of anything to influencing the codes and standards?
I know that actually Professor Tora Hutchison is really into cold form steel testing, and she's got another test she's looking that's going to go. I believe it's at least 10 stories tall that she's looking at developing and working on. So I think the plan is ultimately to sort of look at taller buildings with cold form steel and try to get code acceptance to be able to go to these taller buildings. I think that's sort of the direction I see it going. I also, again, like I said earlier, I question the whole use of Omega on those studs. I mean, when you looked at those walls, you could see the compression posts were more like a compression post shear wall than actually just compression posts. So, they're all welded together and they're fairly stiff. So and that would be an area. Now, whether, someone's going to carry the ball, obviously to get code approval, somebody has to, do the work and the legwork to get it before the committees and get it all approved. And, that's something that I don't necessarily get into. I know there are engineers like Ron Hamburger and stuff like that have carried that ball quite a bit. And I think Tara is certainly looking at some of that, but how it's going to get in the code and how soon is hard to say. It's really hard to say how that's going to happen.
Great.
And we're also involved on that project. And something interesting too that Tara is doing on the preliminary testing is being able to put sheet metal underneath the sills and the headers of the windows and doors and try to find out the shear value that would take on an exterior wall or a corridor wall, where you can take advantage, especially on the exterior walls. What happens if you put sheet metal all across on top of the window and above the window and get some of those shear values? So yes, there's some preliminary testings being done right now, and 10-story is the task to go to.
All right. Well, look, I think, and the last question is really kind of a question for me is will the recorded webinar be available to view, and where? We will make that available to everybody who is on this call and registered, and then of course on our websites. So again, I would like to express my appreciation to Harry and Diego and all the good work. This has been a great project. A lot of good information came out of it, and again, thanks to everybody in the audience who joined us today.